We go further. Question number 26 about Joules heat, Joule effect, Joules law and Joules constant. To understand about all these terms, you please consider a closed circuit shown in the diagram, in which one battery of terminal voltage capital V, one metallic wire of ohmic resistance capital R and one key are connected one after another to form a closed loop. Okay, fine. Now tell me, what do you mean by ohmic resistance? A resistance which is determined from Ohm's law is called ohmic resistance. And as such also you know, metallic wires, that is good conducting wire, will obey Ohm's law. Fine. Now in this loop, what should be the direction of conventional current? Outside the battery, in the outer part of the circuit, the direction you must show from positive to negative terminal of the battery. Correct? Fine. This is called conventional direction of electric current. But actually speaking, the current is produced by the motion of free electrons. Now you know how is that motion? It is called drifting motion, because electrons are just moving with a great difficulty. Such a motion is called drifting motion. Actually what happens? From this negative terminal of the battery, free electrons are pushed away this way, and that is why these free electrons are drifting in this conducting wire, and ultimately they reach to the positive terminal of the battery. Correct? And in just opposite to this direction, we are supposed to show the direction of electric current. Correct? Fine. Now tell me, for this entire wire, you just consider the ohmic resistance to be capital R. Okay? But that resistance we are just showing according to textbook like this. So what you should understand, from this point onwards till this point, this wire has got no resistance. You just consider like that. Similarly, this part of the wire has got no resistance. Correct? So whatever resistance is connected across the battery, it is simply capital R. Fine. Now tell me, what do you mean by terminal voltage of a battery? In a very short word, you can say it gives you net amount of energy to 1 unit negative charge when it comes out of negative terminal of the battery. Fine. For 1 unit negative charge coming out of this negative terminal, if the net amount of energy supplied by the battery is capital V, then for Q unit of negative charge, what will be the net amount of energy supplied by the battery? V into Q. V into Q. For 1 unit charge, it is V. For Q unit charge, it will be V into Q. So I am writing here V into Q. This much is the net amount of energy supplied by the battery to Q unit of negative charge when it comes out of negative terminal. Correct? Fine. Now that amount of energy is in the form of electrical energy. Let it be shown by symbol capital W. Okay? Now with that energy, the free electrons arrive here at point B. At that time, they have this much amount of electrical energy. But now they will have to pass through the material of metallic wire. And don't you know, at room temperature, inside the metallic wire, there are so many positive ions which are performing thermal vibrations about their equilibrium positions. Correct? Now tell me, in the space between the oscillating ions, when electrons are making their drifting motion, at that time they will collide often and often, again and again with those positive ions. And when definitely electrons will collide with the ions, at that time they will lose some part of obtained electrical energy. Correct? Fine. So in each collision, electron is just losing some part of its energy. Fine. Now after that, what will happen? After gaining energy from the electrons, those oscillating ions will start oscillating violently. That is, they will start oscillating with bigger amplitude and bigger frequency. When oscillations are made larger and faster, at that time they are just making their random motion more violently. And have you not studied in 11th standard? The energy associated with random motion of the constituent particles of a body is nothing but amount of heat energy of that body. So, right now there is some heat energy generated in that conducting wire, and its presence was noted first of all experimentally by one scientist with name James Prescott Joule, and that is why that heat in the memory of that scientist is called Joules heat. That is why I am writing here Joules heat. Okay? And once the Joules heat is produced, after that naturally temperature of that metallic wire will increase. This very phenomenon is known as Joule effect. Heat energy is called Joules heat and the phenomenon is called Joule effect. Correct? How would you define it? I mean, how would you give the statement? Very simple. Whenever electric current is passed through any conductor, then due to its resistance, some amount of heat energy is generated in that conductor. This heat is called Joules heat and this very phenomenon is called Joule effect. I repeat, whenever electric current is passed through any conductor, whatever amount of heat energy is generated in it due to its resistance is called Joules heat and this very phenomenon is called Joule effect. Got it? Fine. Tell me, what was the net amount of energy negative charge had at point B? It was W equals to VQ. That energy was in the form of electrical energy, correct? But then that negative charge had passed through the resistance of that metallic wire, and in doing work against that resistance, the negative charge had lost its total energy. That is why the energy of that negative charge when it comes at point A has become 0. So, what is the amount of energy lost by that negative charge as it passes through this ohmic resistance? It is this minus this, correct? That is VQ. So, I am writing W equals to VQ, which gives me loss of electrical energy, correct? Now, this V as it is, but Q equals to IT because I equals to Q by T, correct? So, Q will be IT, fine. Now, V equals to IR according to Ohm's law. I told you this resistance is determined from Ohm's law, it obeys Ohm's law. Then you know V equals to IR, voltage equals to current into resistance. Then I am placing V equals to IR, IT as it is, I into I, that is I square into R into T, correct? Tell me, if you take this current in ampere, resistance in ohm, time in second, then naturally this electrical energy will be in joule, correct? Fine. Now, I told you this much amount of electrical energy is getting transformed into heat energy, and that heat energy I am showing by symbol capital H. If you have got pure ohmic resistance in the circuit, nothing else, only pure ohmic resistance, then this electrical energy is completely transformed only into heat energy, and that heat energy I am showing by symbol capital H. So, I am writing same amount here also I square RT, correct? And still this is also in joule, okay? But generally it is a tradition to show amount of heat energy in calorie. So, let us convert this joule into calorie, and that conversion is done using one constant which is called Joules constant. That constant also was determined experimentally by the same scientist, Mr. James Prescott Joule. Now, what is that? I am showing you. Practically found value of Joules constant is capital J equals to 4.186 joule per calorie. This is exact value. If you want approximate value, you may just write 4.2. Okay, fine. Now, what does it indicate? It indicates that per 1 calorie, the amount of mechanical energy is 4.186 joule. So, using this physical constant, we can establish the equivalence between heat energy and mechanical energy. That's why it is called mechanical equivalent of heat. What is it called? Mechanical equivalent of heat, correct? So, another name for Joules constant is mechanical equivalent of heat, from the value of which we can find out given amount of heat energy is equivalent to how much amount of mechanical energy. Okay, fine. From here we can see 1 calorie is equivalent to 4.186 joule. If 1 calorie is equivalent to 4.186 joule, meaning thereby whenever you require to convert calorie into joule, you should multiply by this value, correct? But if you want to convert joule to calorie, then you should divide by this value, correct? This amount of heat energy right now it is in joule. I want to convert it into calorie, then joule to calorie you should divide by this much value, that is 4.186. So, the same formula written here, but now that term I am dividing by 4.186 and then you should write calorie. Okay? Joule is converted into calorie by dividing by this factor, got it? But the same factor can also be represented by symbol capital J, that is Joules constant. So, in place of this I can write capital J, correct? Fine. Now, let us go for what is called Joulean power. Generally, power is defined as energy per unit time, correct? But because you want to define Joulean power, let this be Joulean heat. Okay? Joulean heat generated per unit time is called Joulean power. Simple. Joulean heat generated per unit time is called Joulean power. Now, find out H upon T from here. Take this T in the denominator. So, H upon T will be I square R. H upon T will be I square R, correct? And if you want to write SI unit, then here it is watt, here it is joule per second, here it is ampere square into ohm, got it? Fine. Now, let us go for Joules law. Which result is called Joules law? I am showing you. Here you had considered some metallic wire. Let it be given metallic wire at a given temperature, then its ohmic resistance can be considered to be constant. I have written here, for given metallic wire at a given temperature, its ohmic resistance is constant, correct? When R is constant here, look, when R is constant, if you remove, then mathematically you can write P proportional to I square, P proportional to I square. So, P is proportional to I square. This very result itself is known as Joules law, correct? This current, when it is flowing, if it is not changing its direction, not changing its magnitude, we will call it steady current. We will call it steady current. So, in this Joules law, remember, this is not simply current, it is a steady current. It is a unit directional current with constant magnitude. Okay, fine. Now, how would you give the statement of Joules law? Very simple. Whenever a steady electric current is passed through a given metallic wire at a given temperature, the amount of Joulean heat per unit time generated in that wire is directly proportional to square of that steady current, full stop. This very statement is called Joules law. I repeat. Whenever steady electric current is passed through a given metallic wire at a given temperature, comma, amount of Joules heat generated in that wire per unit time is directly proportional to square of that steady current, full stop. This very statement is called Joules law. And now, you know Joules heat per unit time. Joules heat per unit time is nothing but Joulean power. So, in terms of Joulean power, if you want to define, you can just give the statement this way. Whenever steady electric current is passed through a given metallic wire at a given temperature, comma, Joulean power generated in that wire is directly proportional to square of that steady current, full stop. This very statement is called Joules law. Got it? Fine. Now, we go for formula of electrical power. Now, you know power is nothing but energy per unit time. but because you want to define electrical power, this must be electrical work done or electrical energy, correct. So, amount of electrical energy per unit time is called electric power. I repeat, amount of electrical energy per unit time is called electrical power. Fine. Find out W upon T from here. W upon T from here. First of all, from here, W upon T. W upon T will be V into I, correct. W upon T will be V into I. Here it is. W upon T will be V into I. Got it? Fine. And if you want to find out W upon T from here, W upon T, it will be I square into R. Here it is, I square into R, correct. And don't you know Ohm's law, V equals to IR, find out I, it will be V upon R, I equals to V upon R, I equals to V upon R, put it here, then V into V upon R, what is it? V square upon R, correct. So, there are 4 formula for electrical power. First is W upon T, second is V into I, that is voltage into current, third is I square R, that is current square into ohmic resistance, and fourth formula is V square upon R, square of voltage divided by ohmic resistance. How would you remember all these 4 formula? Very simple. P equals to W upon T, V into I square into R, V square upon R, correct. I repeat, P equals to W upon T, V into I square into R, V square upon R. Can you remember this way? Simple? Fine. Now, similar to these 3 formula, you had studied 3 formula for centripetal or radial acceleration of that particle performing uniform circular motion in 11th standard. Just recall those 3 formula. Symbol for radial acceleration was AR, and the 3 formula were like this: omega into V, omega square R, V square upon R. Omega into V, omega square R, V square upon R, correct. Give me identification of each quantity. What is this omega? Angular speed. What is V? Linear speed. Again, this small r is common radius of the circular path along which the particle is performing uniform circular motion, correct. These 3 formula are quite similar to these 3 formula, but the interpretation of different symbols is different. So, please do not get confused, and for that you must do lot of revision. Please do it, okay, fine. Now, my dears, let us go for question number 27. It is about practical applications of Joules heat. My dears, every coin has got 2 sides. Similarly, Joules heat also has 2 sides. I mean, it has advantages also, it has disadvantages also. Like a fire, fire has its own advantages and its own disadvantages. Similarly, with Joules heat also. How Joules heat is disadvantageous? I am showing you. In the majority phenomena of physics, where there is a transformation of energy from one form to another form, we find that there is a production of some amount of heat energy. So, in those cases, the production of heat energy is inevitable, means you cannot stop it. Of course, you can minimize through some ways and means, but you cannot stop it, okay. So, in all those phenomena, wherever production of heat energy is not desired and yet it is getting generated, then it is a wastage of energy in the form of heat energy. For example, you will be taught in 4th semester about sending or transmitting electric power at long distances. At that time, you will be taught that transmission of electric power at long distances is made at very high voltage just to minimize the heat loss. Normally, we call it ohmic loss, correct. So, just to minimize the ohmic loss, we prefer to transmit that electric power at very high voltage. Let me give you second example where production of heat energy is not desired. For example, at our home, we are running electric motor, and for that we are supplying electrical energy to fetch water from lower tank to upper tank. But you will be surprised to know whatever amount of electric energy we are supplying to the electric motor, its majority part is wasted in the form of heat energy. Very little energy is really utilized in the form of mechanical energy, which really fetches the water from lower tank to upper tank. Okay? So, I mean to say, wherever production of heat energy is not desired and then also it is getting produced, then you can say it is a wastage of energy in the form of heat energy, which normally we call ohmic loss. Got it? Fine. Now, let us see some positive aspects of Joules heat, that is some advantages of Joules heat, where it is really expected, where it is really desired. Come on, I am showing you one by one all the examples. Let us talk about some of the household appliances, say OTG, that is oven, toaster, griller, oven, toaster, griller. This is that electrical appliance in which we expect, we desire to have production of only one form of energy, and that is heat energy. There we expect, there we desire that whatever amount of electrical energy we are supplying to that instrument, to that device, the same amount must be getting transformed completely into heat energy. That is what we desire. Okay? So, that is the advantage of Joules heat, because using that heat energy only we can use this device. Okay? Fine. Then electric iron. For running electric iron, we just supply electrical energy to that, and that electrical energy supplied to that is getting transformed into heat energy, which makes the bottom plate very hot, and that too very quickly. Okay? Fine. Then any heater, might be room heater, might be water heater, but just to run it we supply electrical energy, and there we expect that that electrical energy must be getting transformed into heat energy. Fine. Now, let us talk about light bulb. For running any electric bulb, what we do? We just pass some current through the filament of that bulb. Normally, filament is made up of that sort of material whose melting point is very high. For example, you consider filament made up of tungsten. Chemical symbol for tungsten, remember it is capital W. Its melting point is very high as 3380 degrees centigrade. Okay? Now, tell me, when you supply electric current to the bulb, at that time it produces lot of Joules heat, and because of production of very large amount of heat, it raises its temperature very quickly to some limit, and then after partly that energy is getting transformed into light energy. Okay? So, whatever electric energy we are supplying to the bulb, its majority part is reproduced in the form of Joules heat, and little part is converted into light energy. And so, we can say function of bulb will be possible only when the light energy will be emitted, but light energy is getting emitted only at a temperature beyond certain limit, and for that we desire that lot of amount of heat must be produced, and that too very quickly, and that is the advantage of Joules heat produced in the filament of the bulb. Correct? Fine. Now, in textbook here they have written one sentence that in practice such electric bulbs, they give 1 candela light energy per 1 watt electrical power. My dears, it is not true. It is not the proper way of writing that statement, because candela is not the unit of light energy. Candela is the unit of luminous intensity. Then you will be asking to me, I mean you may have a question in your mind, what is that luminous intensity? For that I am just giving you some extra explanation, not in your syllabus, just for your kind knowledge and satisfaction. Okay? Look here. Now, my dears, you just consider a source of light which emits infrared light, visible light and ultraviolet light also. Correct? Among these three parts, only visible light is that light with the help of which things are made visible to all human beings. Okay? And other two parts, infrared and ultraviolet, they are invisible light for human beings. Correct? but at present we are considering all the three parts: infrared, visible and ultraviolet. Now, for that source, how the power of radiation is defined? It is defined this way: total light energy emitted from a given source per unit time is called power of radiation for that source. Simple. And its SI unit is joule per second, that is watt. Simple. Now, we restrict our discussion only for that source which emits visible light, For example, light emitted from any electric bulb, light emitted from this fluorescent tube, that is tube light, correct? They emit visible light, fine. Now, when you incident a visible light on any surface, how much that surface will be illuminated? What will be the brilliance observed on the surface? That depends on three factors. First, it depends on power of that source from which visible light is emitted. Secondly, it depends on distance between that source and that surface. And thirdly, it depends on direction of incidence. We find that if direction of incidence is perpendicular to the surface, then that surface is getting illuminated with maximum amount. Okay, fine. Now, all these factors are being studied in one branch of physics which is called photometry, Okay. Now, we discuss some physical quantities in that branch, and first we are taking right now luminous flux. What do you mean by luminous flux? Look here. It is shown by symbol phi. It is defined by this ratio, in which this EV means visible light energy and this is time. Okay. So, how will you define luminous flux from this formula? Very simple. Visible light energy emitted from a given source of visible light per unit time is called luminous flux coming out of that source. I redefine: visible light energy emitted from a given source of visible light per unit time is called luminous flux coming out of that source. Correct? Fine. Now, here for luminous flux, we have given another SI unit called lumen. Its symbol is small l, small m. Okay. Now, you may have a question, why we have given other unit? Why can't we use watt? Correct? See, if we use watt, then somebody will be misguided. Then he will think that it is a light which is infrared also, visible also and ultraviolet also. Correct? But actually, this lumen is defined only for visible light. Correct? That is why another unit is given. For example, calorie and joule, both are the units of energy, but calorie we use normally in case of heat energy. Correct? And there is a relation between calorie and joule. We had already seen that relation. 1 calorie equals to 4.186 joule. Correct? Similarly, here lumen is also some sort of power, watt is also power, then there must be some relation between them. Yes, there is a relation, and that relation is this. Look, 1 lumen is equal to 1 upon 685 watt. 1 lumen is how many watt? 1 upon 685 watt. Now, this relation is established for a monochromatic light having this much wavelength, 5555 angstrom, and color wise we find that color to be yellowish green or greenish yellow, or you can say yellow green light, okay, fine. You may have a question that why we are selecting this particular wavelength. Correct? The reason is that human eye has maximum sensation of sight for this particular wavelength. Maximum sensation of sight means when this particular light with this particular wavelength is made incident on the eye, on the human eye, then it produces maximum sensation. Okay? On the optical nerves, its sensation produced is maximum. Okay? That's why we are selecting this particular wavelength. Got it? Fine. Now, from here we can say 1 watt power of radiation will be equal to 685 lumen. You can transfer this here. So, 1 watt power of radiation will be equal to 685 lumen. Correct? Now, let us go for luminous intensity. Luminous intensity. It is shown by symbol capital I. It is ratio of luminous flux to solid angle. Ratio of luminous flux to solid angle. Now, how is it to be defined? I am showing you. Consider a point like source of visible light at the center of the spherical surface, and you just consider some sort of solid angle, say omega. With measurement it is omega, and through this solid angle the luminous flux coming out of the source is suppose phi. You divide this total luminous flux by this total solid angle, then you will get luminous flux per unit solid angle, and the same ratio is now known as luminous intensity of a given source in a given direction. How will you define it? Luminous flux obtained out of a given source of visible light per unit solid angle in a given direction is called luminous intensity of that source in that direction. I repeat, luminous flux coming out of a given source of visible light per unit solid angle in a given direction is called luminous intensity of that source in that direction, shown by symbol capital I. What about its SI unit? Its SI unit is candela, and symbol of candela is small c small d, small c small d. Okay? Write SI units on both the sides. For luminous intensity it is candela, that is small c small d. For luminous flux it is lumen, small l small m. For solid angle SI unit is T radian, small s small r. Correct? Fine. Now, just re-examine that sentence given in the textbook. Now, what we should understand from that sentence, actually the information is like this. If you take any electric bulb which is normally used in practice, then they emit that sort of light which has luminous intensity 1 candela per 1 watt electrical power consumption. Got it? Now, 1 candela is how much? 1 candela is how much? 1 lumen per steradian. Meaning thereby, if you have kept that source over here, and if this solid angle is 1 steradian, then this luminous flux would be 1 lumen. Correct? And 1 lumen is how much? It is 1 upon 685, that many watt. But remember, this is the watt, is not the unit here for electrical power, this is the unit for power of radiation. So, you are going to take 1 upon 685 times watt, but that watt is right now power of radiation. In the textbook, what have they done? When the bulb consumes 1 watt electrical power, at that time they emit that sort of light which has luminous intensity 1 candela. Got it? So, that 1 watt is electrical power, and here this 1 watt is power of radiation. Okay? Do not get confused. Now, we go for universal use or application of Joules heat. When we talk about universal application of Joules heat, we should regard about fuse. You must have heard this name, this word fuse. But what is that? I am showing you. See, in Ahmedabad, the electrical power is supplied by Torrent Power Limited, correct? But if there is some problem, there is some fault in that company, then the power delivered at our home will have some voltage fluctuations. If voltage goes down beyond the standard value, no problem. but if voltage level goes up beyond the standard value, then it may create problem. For example, suppose you want to run this television set at our home, and for that we are supplying AC power. The power delivered at our home is AC power. This is the symbol for AC source. Fine. Now, if there is a voltage fluctuation and voltage exceeds beyond a certain limit, then it would send current also through this television set beyond the tolerable limit. If current passing through this TV set is more than tolerable limit, naturally it will cause permanent damage to this television set. Okay? So, then how to protect the precious costly household appliances? For that purpose, what we do, in the way we just connect some fuse wire made up of that material having low melting point, for example, made up of iron or aluminum or lead, correct? These materials have got low melting point, and then its wire we just connect here. What is the benefit? What is the advantage? When the voltage level will increase beyond a certain level, then the current passing through this TV set will increase beyond its tolerable limit. But at that time, that excess current will be passing through the fuse wire, and as soon as the current is passing, excess current is passing through the fuse wire, then lot of amount of heat energy will be produced in this fuse wire, which we call Joules heat. But then that excess amount of Joules heat will increase its temperature beyond its melting point, and as soon as the temperature is increased beyond a melting point, naturally this wire will get melted, correct? Once this wire is getting melted, then after the circuit is becoming open circuit, and through this open circuit no current can flow. When no current is flowing through this TV set, naturally it will be saved from the possible damage. Okay? So, that is how we are using fuse wires to protect the household appliances. Okay? We can save them against the voltage fluctuations. Okay? We can save them from the possible damage. Got it?